Hello, I'm Michelle Kreml, and today we are going to review some prerequisite skills needed to be successful in the IB Math Analysis and Approaches course. We're going to start with numbers by simplifying some fractions. So first we have 3/4 plus 1/2 minus 5/6. What we want to do here is get a common denominator. The common denominator for 4, 2, and 6 would be 12. So we're going to rewrite each fraction using a denominator of 12. 3 out of 4 is 9 out of 12. 1/2 is 6 out of 12. 5/6, 10 out of 12. Now that we have a common denominator, we're going to just combine the numerators. So that 9 plus 6 minus 10, that is 15 minus 10, or 5 out of 12. 5 out of 12. For the next problem, we have 7/8 divided by 2, and dividing by 2 is the same as multiplying by 1/2. When we're multiplying fractions, we multiply our numerators. 7 times 1 is 7. We multiply our denominators. 8 times 2 is 16. That fraction cannot be further reduced, so our final answer is 7/16. For the next problem, we have 1/3 raised to the power 4. Then we're going to subtract 4/3. So 1/3 raised to the power 4 is the same as 1 raised to the power 4 divided by 3 raised to the power 4 minus 4/3. So we have some options here. What I'm going to do is get a common denominator, and I'm going to do that by multiplying my second fraction by 3 cubed. Then I'm going to have 1 to the power 4, which is 1, over 3 to the power 4, which is 81, minus 4 times 3 cubed. So that's 4 times 27, over, now 3 to the power 4 is also 81. We have this common denominator of 81, so now we have to simplify the numerator. 4 times 27. Well, 2 times 27 is 54, and if I multiply that by 2 again, I get 108. So this is going to be negative 107 over 81. Next, we have 8/64 raised to the power 2/3. When you have a rational exponent as your power, what you want to do usually is take the root first. The top number is the power. We're going to raise this to the power 2. But the bottom number here in the denominator, that's the root. And if we square first, if we raise the power 2 first, we're going to make our numbers a lot larger and then have to take the cube root. So it's usually easier to do the root first because you're making your numbers smaller. Then you can raise them to a power. So I'm going to do the root first. The cube root of 8 and the cube root of 64. Those are perfect cubes, so this one is going to be easy. But first let me write this a different way just to make sure everyone understands what's happening here. 8/64. Well, first of all, I could reduce 8/64 to 1/8. That would make this problem very simple. But I'm not going to do that because I want to review how to do a little bit more complicated problem. But the easiest way to do this one, I think, is to start by reducing 8/64, and then we can very easily raise it to the power 2/3. But 8/64 to the power 2/3, we're going to square it, and we're going to cube root it. So raising something to the power 1/3 means taking the cube root. And we have this property of exponents. When we have a power raised to a power like this, we multiply our exponents. 2 times 1/3 gives me that 2/3, my rational exponent. But I can also, we know that 2 times 1/3 is the same as 1/3 times 2. So I can also think of it like this, raising it to the power 1/3 first and then squaring it. That would give me an equivalent answer. So that's what I'm going to do. I'm going to take the cube root first. The cube root of 8 is 2. The cube root of 64 is 4. And then we're going to raise that to the power 2. So now I'm going to reduce my 2/4 to 1/2. I'm raising that to the power 2, and I'm going to get 1/4. Okay, so final answer is 1/4. I went about the long way of doing this. As I said, it would be easier just to start by reducing 8/64 to 1/8 and then raise that to the power 2/3. 1 raised to the power 2/3 is just 1 because we're going to square 1 and then we're going to take the cube root of 1. We're still going to get 1. 8 to the power 2/3, you want to do the cube root first. The cube root of 8 is 2. Then we're going to square it, raise it to the power 2. 2 raised to the power 2 is 4. So we get a final answer of 4. So you can see I did that much more quickly the second time. All right, now we're going to simplify some fractions that are inside of a square root. So first thing I'm going to do, and again, we have options. You don't have to do it exactly the way I'm doing it here. But the first thing I'm going to do is I'm going to simplify 3/5 squared, and that's going to give me 9/25. And then 4/5 squared, that's going to give me 16/25. Now I have two fractions with the same denominator, so I can combine this. The 9 plus 16 gives me 25. 25/25 is 1, so this is equivalent to the square root of 1, which is just 1. Okay, next we have 1 minus 2/3 to the power 5. We're going to divide that by 1 minus 2/3. So in the numerator, 1 minus 2 to the power 5 is 32. 3 to the power 5, I'm going to leave that for the moment because I don't know that off the top of my head. 3 to the power 4 is 81, so it's 81 times 3. But then in the denominator, 1 minus 2/3, I'm going to think of this 1 right here as 3/3. With that common denominator, I can subtract those fractions. 3/3 minus 2/3 equals 1/3. And now to simplify this, again, I have some options. I can simplify the numerator some more and try and get just a single fraction in the numerator. But that's not what I'm going to do here. I am going to say dividing by 1/3 is the same as multiplying by its reciprocal 3/1. So dividing by 1/3 is the same as multiplying by 3. Now I can distribute that 3. So that's going to be 3 minus 3 times 32 over 3 to the power 5. Normally I would just do this in my head, but let me write it down so you can see what I'm thinking. 3 times 32 over 3 to the power 5. So this 3 right here is going to cancel with one of the 3's down here. Gives me 3 to the power 4, which I know is 81. So 3 minus 32 over 81. Now to continue simplifying this, I need to get a common denominator. So I would need to multiply 3 by 81. Okay, 3 by 81. 3 times 81, we're doing all this without a calculator. So one way to think about 3 times 81 is to distribute. Think of the 81 as 80 plus 1. So it's 3 times 80 plus 3 times 1. That's 240 plus 3. When I'm doing that mental math, that's normally how I'm thinking about 3 times 81. So it's 243 over 81 minus 32 over 81. All right, we have common denominators, so we're going to combine those numerators. Now I have to do 243 minus 32. So that's going to be 211. Wait, let me double check that. 243 minus 32. Yeah, 112. 211 over 81. Next, we're going to review factoring. There are different ways to factor, so one method doesn't work for all problems. We want to do some recognition here, and hopefully you have practiced these factoring patterns enough in the past that you will recognize the patterns when you see them. So the first one is the difference of two perfect squares, and that's pretty easy to factor. I know if I have a squared minus b squared, that's going to factor as a plus b times a minus b. So I'm going to use that factoring rule here for the first one, because this is 3x squared minus 4y squared, like that. So this factors into 3x plus 4y times 3x minus 4y. The next example is also the difference of squares. We have two perfect squares here. the x is squared, and then the x plus h is squared. Difference of two squares. So that's going to factor as x plus h times x minus x plus h. Now we have to be careful here. I'm subtracting x plus h, so I need an extra set of parentheses there, otherwise I may not distribute that negative properly. Okay, so continuing to simplify this, x plus h right here is 2x plus h. Right here I'm going to distribute that negative, so I'll have x minus h, like so. And if I write it in fully factored form, that's not wrong as it is right now, but normally we would put the negative h in front, then 2x plus h, like so. Okay, the next one is not the difference of squares. There's a different pattern here. This is a trinomial, and the first thing I'm going to do is rewrite it in a different order. So I have my highest exponents first and then go in descending order. Negative x squared minus x plus 20. Now it's more complicated to try and factor this with a negative leading coefficient. So what I'm going to do first is just factor out the negative 1, and this becomes x squared plus x minus 20. Okay, now I'm going to try and factor x squared plus x minus 20. And there are different methods for factoring trinomials. I'm going to do it mentally, just the guess and check method, because I know I'm looking for two numbers that multiply to 20 and add to a positive 1, and that's pretty easy to just think of, 4 and 5. So I have x, and x is what's giving me x squared right here. Then the 4 and the 5 is going to multiply to give me the 20 right here, and I have to get my signs right. I need to get negative 20 when I multiply. I need to get positive 1 when I add, so it's going to be plus minus, like so. And then I always like to multiply it back out just to check, because it's easy to make a mistake with the signs. So first times first is x squared. Outer product is 5x. Inner product, negative 4x, so that adds to 1x. And then last times last, negative 20, so that looks correct. The next example, we also have a trinomial. It's not quadratic, but we can treat x squared as a new variable and put it in a quadratic form. So if I say, for example, y equals x squared, then x to the power 4th is y squared. 10x squared is 10y, and then plus 9. So now I can try and factor this trinomial. And just thinking about it in my head, multiplying to get 9, adding to get 10, it's going to be 1 and 9. 1 and 9. So y and y is going to give me the y squared. 1 and 9 multiplies to give me 9. Now I need to get negative 10 in the middle. So the outer product, negative 9y, inner product, negative 1y, that's going to add to be negative 10y. But my final answer, I need to rewrite it back in terms of x. The y was just a placeholder for x squared. So this is x squared minus 1 times x squared minus 9. Now I'm not finished factoring this because each one of these factors can be factored further. X squared minus 1 is the difference of two perfect squares. It factors as x plus 1, x minus 1. X squared minus 9 is also the difference of two perfect squares. It factors as x plus 3, x minus 3. So now this is fully factored. In our next example, we have 2x squared minus x minus 6. 2x squared minus x minus 6. So I'm just going to go ahead and try and factor this trinomial using mental math or the guess and check method. 1 times 2 is really the only way I'm going to get 2x squared. I mean, technically it's not the only way, but using integers, this is going to be the only way. So this is going to be x and 2x. That way, first times first gives me 2x squared. Now to get the negative 6, it could be 1 and 6, 1 times 6. It could be 2 times 3. So I'm looking for a combination of these two numbers and these two numbers to give me a -1 in the middle, or possibly these two numbers. Okay, so it looks like, I'm just checking, so it could be, no, it could be 1 times 2 and then 2 times 3. 1 times 2 is 2, 2 times 3 is 6. Nope, that's not going to give me a 1. So it could be 1 times 3 and 2 times 2. 1 times 3 is 3, 2 times 2 is 4, and the difference is 1, so I think that's it. I need the 2 to get multiplied by 2, so that goes there. And I need the 1 to get multiplied by 3, so that goes there. Now I have to get my signs right. I need a -6 when I multiply, so one of these has to be positive and one of them has to be negative. I want to get -1 when I add, so I want -4x, positive 3x, like so. If I FOIL this back out, x times 2x is 2x squared. Outer product, 3x. Inner product, -4x. And then last times last, -6. That simplifies to -x, so that is correct. Number 9, we have the difference of cubes. These are perfect cubes. 8x cubed is 2x cubed. 27y cubed is 3y cubed. We have the difference of cubes. So I'm going to use the pattern for difference of cubes. If I have a cubed minus b cubed, that factors as a minus b times a squared. There's an acronym here that some people like to use. SOAP. So we start first factor with the same sign. Then the next one has the opposite sign. When I talk about sign, I'm looking at right here, minus. So this is the same sign, it's minus. This is going to be the opposite sign, so it'll be plus. And we're going to multiply these cube roots together. And then the last one is always positive. We're going to square the second root. So we square the first root, multiply the two roots together, square the second root, like that. That's our pattern. So we're going to have our first root, 2x, same sign, minus the next root, 3y. Then we're going to square the first root, 4x squared, use the opposite sign, plus, multiply these two roots together, multiply them together. So 6xy, and then square the second root, 9y squared, like so. And this is not further factorable, so that's our final answer there. Next one is also the difference of cubes. We will follow the same pattern. We need our first root, x plus h, same sign, so it'll be plus. The next root, which is x. Let me write down the roots so I don't get confused. X plus h is the first root, cube root, and then just x is the next cube root. Okay, so first root, x plus h. We use the same sign. Actually, this is the sign right here, so I did make a mistake. This should be a minus. And then the next root is x, like so. Okay, we're going to square the first root, so x plus h squared. Opposite sign, opposite of this, so it's going to be plus. I'm going to multiply my two roots together, so x times x plus h. And then I'm going to square my second root, x squared, like so. Now there's more simplifying for me to do here. X plus h minus x, right here. X plus h minus x is just h. And then right here, I'm going to FOIL this out. X squared plus 2xh plus h squared. Okay, then I'm going to distribute the x here. So I'll have plus x squared plus xh, and then this term, plus x squared. So I have some like terms that I can combine. Here, here, here. And And let's see, we have 2xh, we have xh. Okay, so h times 1, 2, 3 x squared plus 2xh plus xh is 3xh, and then plus h squared. Now I could distribute this h here, but the directions say to factor. So I don't want to distribute, I want to factor out as much as I can, leaving this as my final answer. Okay, next we have number 11. We're factoring. The instructions say factoring. So I'm looking at, there are two terms here. Two terms. Here's the first term. Here's the second term. So I'm going to look to see what do they have in common. Do they have any common factor? And then I'll factor that out. So I see that they have a common factor of x. More than that, they have a common factor of x squared, because x cubed is x times x squared. And then here there's an x squared. So they have a common factor of x squared. They also have a common factor of x minus 7, but more than that. This is x minus 7 cubed. This is x minus 7 cubed times x minus 7. So what they have in common, the common factor, is x squared times x minus 7 cubed. You're going to factor out the largest thing that they have in common. So you have to go with the smaller exponent because that's what they have in common. Then that's multiplied by whatever is left over. Factoring out means dividing. Factoring out means dividing. So I'm going to look at each term one at a time here and factor out. So let's start here. When we factor out x squared, what's left? If I factor out x squared, there's an x left. If I factor out x minus 7 cubed, then that's gone. So the only thing left in this term now is 3x. 3x. 3x plus. Now we're going to factor out from this term. Okay, I'm factoring out, which means dividing. I'm factoring out x squared, so that's gone. I'm factoring out x minus 7 cubed. When I factor out x minus 7 cubed, what's left is x minus 7 to the power 1. Okay, so this term has a 4, and then this x minus 7. 4 x minus 7, like so. Let's simplify some more. X minus 7 cubed, and then in here we have 3x plus, if I distribute the 4, I get 4x minus 28. These are like terms, they can be combined. So x squared times x minus 7 cubed times 7x minus 28. Now 7 is a factor of 28, so I can factor this further. 7x minus 28, I can factor out a 7. Factoring out means dividing by. I can divide each of those terms by 7. So x squared, x minus 7 cubed, I'm going to factor out a 7, and I'll write that in front. And when I factor out a 7, I'm dividing by 7, dividing by 7. So what's left behind? X minus 4. Okay, so final answer, 7x squared times x minus 7 cubed times x minus 4. And our last factoring problem, 5x squared minus 17x plus 6. Okay, I can just do my guess and check method here. To get 5x squared, that's got to be 1 times 5. There are no other integers that I can work with there. So it's going to be x and 5x. That's the only way I'm going to get 5x squared. Then for 6, it could be 1 times 6 or it could be 2 times 3. So I need to now find the right combination to get negative 17 in the middle. So it could be 1 times 2 and 5 times 3. Oh, I think I got lucky on my first try. 1 times 2 is 2, 5 times 3 is 15. And if I add the 2 and the 15, I'll get 17. So that's it. But I don't always get lucky on the first try, right? I could have said, oh, no, do 1 times 3 and 5 times 2. That's 3 and 10. That's not going to give me 17, and so on. So you just keep trying the different combinations until you find what's going to work. But it's going to be 1 times 2, 5 times 3. The 5 needs to get multiplied by the 3, so the 3 has to go here to get that inner product, 3 times 5. And then the 1, this 1 right here, there's a 1 right there, that 1 needs to get multiplied by 2. So that's in the outer product. The 2 has to go there. I want a positive 6, so it's either going to be, when I multiply the 3 and the 2, I need a positive 6, so it's going to be either plus plus or minus minus. When I add the outer product and the inner product, I need to get negative 17, so it's got to be minus minus. And then a quick check. First times first, 5x squared. Outer product, negative 2x. Inner product, negative 15x. That combines to negative 17x. And then last times last is positive 6. So I know I got that right. All right, so it's x minus 3 times 5x minus 2. In our next example, we have 3x squared minus 7x minus 6. So I'm going to factor this in the same way. 3x squared, 1 times 3. 6 could be 1 times 6, 2 times 3. I'm trying to get 7x in the middle, so I'm looking for the right combination. If I do 1 times 2, 3 times 3, that's going to be 6 and 3. That's not going to give me 7. That doesn't work. So the 1 times 2 doesn't work. I could do 1 times 3, 3 times 2. That's going to be 3 and 6. Those products, I'm looking. These represent inner outer products. So 3 and 6 is not going to give me 7. That's not it. That does not work. Okay, it could be 1 and 1, 3 and 6. That's going to be 1 and 18. That's not going to give me 7. It doesn't work, so it's not the 1 times 1. It could be 1 times 6, 3 times 1. That's going to be 6 and 3. That's not going to give me 7. That doesn't work. None of these combinations worked unless I made a mistake. So that indicates to me that this is not factorable. If it's not factorable, then we can use quadratic formula, although the instructions did say factor. So let me just double check. I may have made a mistake. 1 times 3, 1 times 6, 2 times 3. Let me run through those options again. Okay, so 1 and 1, 3 and 6. That's 1 and 18. Not going to give me 7. 1 and 6, 3 and 1. 6 and 3. 6 and 3, whether I add or subtract, not going to give me 7. 1 and 2, 3 and 3. That's 2 and 9. 2 and 9. 2 and 9, if I subtract, I can get 7. Okay, so that was just a mistake on my part. Now, some trinomials are not factorable. That certainly can happen, but here we're practicing factoring, so that's why I was suspicious. Okay, so my first times first, this represents first times first, by the way. First times first. This represents last times last. And then where I drew the red lines, that represents inner product, outer product. So now that I have this mapped out, I know exactly how to set up my answer. First times first, 1 and 3. So one of the coefficients needs to be a 1. The other coefficient is going to be a 3. Last times last is going to be the 2 and the 3, but I don't know if it should be 2 and 3 or 3 and 2. That's why I need those red lines to help me. Okay, so the 1 has to get multiplied by the 2. That's how I drew my red lines. And the 3 needs to get multiplied by the 3. So the 3 needs to get multiplied by the 3. That's got to be inner product, the 3 and the 3. And then the 1 needs to get multiplied by a 2. That's my outer product. Okay, so one more time. First times first, that's this 1 and 3 right here. First times first. Last times last, 3 times 2, that's this right here. Last times last. Then this is 1 times 2, 3 times 3. That's where I drew my lines here. 1 times 2, 3 times 3. Giving me the inner outer product that I need to make this work. So now I just have to figure out the signs. I need it to be, last times last needs to give me negative 6. So one of these is positive, one of them is negative. When I add inner and outer product, I need to get negative 7x. So I need the 9x to be negative, and I need the 2x to be positive, like that. Now, if I check by FOILing this out, first times first, 3x squared. Outer product, 2x. Inner product, negative 9x. And then last times last, negative 6. So 3x squared minus 7x minus 6. That's what I needed. Okay, so final answer, x minus 3, 3x plus 2. Like so. Number 14. This one's not a trinomial. We have two terms, so what we're going to do is factor out what they have in common, the largest thing that they have in common. So when we're comparing exponents, we're going to factor out the smaller of the two exponents because that's what they have in common. 5x to the power 2/3. That's 5x to the power 1/3 squared, like that. When we have a power raised to a power, we multiply exponents. So 1/3 squared to the power 1/3 squared is the same as to the power 2/3, minus 4x to the power 1/3. Now I can see what they have in common is x to the power 1/3. This is what they have in common, so that's what I'm going to factor out, x to the power 1/3. That's what they have in common. When I factor it out from the first term, factoring out means dividing. So if we're looking over here, think, oh, I'm dividing by x to the power 1/3. When we divide, we subtract our rational exponents. When the base is the same, we subtract those rational exponents. So dividing by x to the power 1/3, I'm going to subtract that exponent. It's going to leave me with x to the power 1/3. Or you might see it more easily here. If I'm dividing by x to the power 1/3, there are two of them. It's squared. There are two of them. So I'm factoring out one of them. It's going to leave me with 5x to the power 1/3. And then from this term, when I factor out x to the power 1/3, that just goes. So minus 4. There's nothing more to simplify here. So that's my final answer. You don't need square brackets. Parentheses are fine. Okay, next one, same thing. We're going to look to see what do they have in common, because there's really only two terms here. And this looks pretty complicated, but there's only two terms. Two terms. So what do they have in common? Well, they don't have an x in common as a factor. They don't. They don't have a 2 in common. So those are going to stay. They both have some power of x plus 3. Some power of x plus 3. We're going to factor out some power of x plus 3. What power do we factor out? We factor out the smaller of the two powers. The smaller power is what they have in common. So the powers are negative 1/2, positive 1/2. We're going to factor out the negative 1/2. That's what they have in common. X plus 3 to the power negative 1/2. Now, we're going to see what's left behind when I factor that out. Factoring out means dividing. So I'm dividing by, think of taking this whole term and dividing it by x plus 3 to the power negative 1/2. Well, that just cancels out. All that's left is the x. X. So that one was easy. This one's a little trickier. This next term, we're factoring out x plus 3 to the negative 1/2, so I'm dividing by x plus 3 to the negative 1/2. When I divide, I'm subtracting my exponents. The bases match, subtracting the exponents. 1/2 subtract negative 1/2. There's a double negative there. 1/2 minus negative 1/2 is 1/2 plus 1/2 is 1. Okay, so we have this plus right here. Is this plus? The 2 remains, and then I have x plus 3 to the power 1. To the power 1. Okay, let's simplify further. X plus 3 to the power negative 1/2. X plus, distribute the 2. 2x plus 6. Combine like terms. X plus 3 to the power negative 1/2 times 3x plus 6. Oh, 3x plus 6 can be factored further. There's a common factor of 3. So I'm going to factor out a 3 from this term right here. And I'll write that in front. 3 times x plus 3 to the power negative 1/2 times, factoring out a 3 means dividing by 3, so this is x plus 2. Now we can also write this as 3 times x plus 2 and move the x plus 3 to the negative 1/2 into the denominator because it has a negative exponent. We can move that into the denominator and make it a positive exponent. So this is also acceptable as fully factored form. Okay, next we are simplifying algebraic fractions. These are fractions that have variables in them. Okay, so for the first one here, we're going to factor out what the numerator, terms in the numerator have in common. X times x plus 3 over x squared. And now there is a common factor that we can remove. When you have factors in the numerator and denominator, only cancel them out if they're factored. Factors. Only cancel out common factors, not just numbers or variables, but factors. That x is factored out. X is a factor in the numerator. There's also an x as a factor in the denominator, so those cancel out, leaving us with x plus 3 over x. All right, next we have some common factors in the numerator, the terms in the numerator. They both contain an a, they both contain a b, so I'm going to factor out ab. Factoring out means dividing, so this first term I'm going to divide it by ab. ab squared divided by ab is just b. Minus, and then ba squared divided by ab. Right here I'm factoring out ab, so I'm dividing by ab. That's going to leave a. And then in the denominator, a minus b. Now, we can go further with this. b minus a and a minus b are not the same factor, but they are opposites. They're opposites. One is the opposite of the other. So I can factor out a negative 1 from this term right here. If I factor out a negative, then b minus a turns into a minus b. Now I have a common factor. This is a minus b right here is a factor. It's factored. A minus b here is a factor, so it cancels out. And final answer, negative ab. Negative ab, like so. Okay, next, x squared plus x minus 6. We can try and factor that. That looks like an easy one to factor because the leading coefficient is 1. So x and x gives me the x squared. To get 6, it could be 1 and 6 or 2 and 3. I'm trying to get a plus 1 in the middle, so it's going to be 2 and 3. I need a negative 6 when I multiply, so one of these is positive, one of them is negative. I need a positive 1 when I add the inner and outer product, so this one needs to be positive and this one needs to be negative. Denominator, x plus 3. Now we have a common factor in the numerator and denominator. So we can remove the common factor, leaving us with a final answer, x minus 2. Number 19, we call this a complex fraction. We have a fraction inside of a fraction. Our numerator contains a fraction. There are multiple ways to simplify complex fractions. The way that I like to do it is to look at all of the inner fractions, look at the denominators, the inner fractions. There's only one inner fraction, so it makes this kind of easy. You take the least common denominator for all the inner fractions, but there's only one inner fraction. So the least common denominator is x minus 1. Then what you're going to do is multiply. So let's take away that equal sign. I'm going to multiply this fraction by that least common denominator over the least common denominator. I'm really just multiplying by a fancy form of 1. X minus 1 over x minus 1 reduces to 1. So multiplying by 1 is not going to affect my answer. I'm going to multiply. Now when we multiply fractions, remember the rule, multiply numerator, multiply denominator. So look, denominator is easy, x times x minus 1. And I'm going to leave it factored like that, x times x minus 1, because I'm hoping I'll have a common factor that I can simplify more. Maybe I will, maybe I won't, but for now, I'm hoping that I will, so I'm going to leave that in factored form. The numerator is a little trickier. You have to distribute. This x minus 1, we have to distribute it here and then here. Okay, if you need to work off to the side, that's a good, careful way to do it. That's fine. So what we're doing first is we're taking this x minus 1 and we're distributing it to this 1. So 1 times x minus 1 is x minus 1. Then we're going to use this sign right here, plus. Now we're going to distribute this x minus 1 to this term right here. Multiply them together. If you need to work off to the side, that's fine. 1 over x minus 1 times x minus 1. That's what I'm multiplying together right now. And that's going to cancel out and just give me 1. Now we can simplify. In our numerator, x minus 1 plus 1 is x. In the denominator, x times x minus 1. Now be very careful here. You can't just cancel this x and this x. I see that mistake a lot. You cannot do that. You can only cancel factors, common factors. And at the moment, this x is not a factor. X minus 1 plus x, that x is not a factor. So don't try and cancel it at that point. But once we simplify it a little bit more, now this x is a factor. Right? We can think of this numerator as x times 1, like that. The x is a factor. And in the denominator, this x is a factor. So now we have a common factor. They cancel out, leaving us with 1 over x minus 1. Okay, next we also have a complex fraction. So I'm going to use the same strategy, look at all of the inner fractions. There's only one inner fraction right here, and take the LCD, so that's going to be just the same thing. Square root of c over square root of c. I'm going to multiply by square root of c over square root of c. So multiply my numerators, multiply my denominators. I have to distribute. The square root of c gets distributed to the a. So a root c. Then here, the square root of c gets distributed to b over root c. And I'm using this sign in the middle here as well. So minus, then I'm multiplying b over root c times root c. These cancel. I'm just going to have b. And then in the denominator, I have c root c. C root c. So I can stop there. The direction said simplify. It's not always clear how far to take it. If there's clearly a common factor, then you need to cancel out a common factor when you're simplifying. But here we can leave it as is. I could also take it a step further if I want to separate this into two fractions. I could think of this as a root c over c root c, and then minus b over c root c. I'm just unadding the fractions together, undoing that. And the only reason I might want to do that is because now that common factor can be removed. So I have a over c minus b over c root c. But honestly, that doesn't look more simple to me than our first answer. So either one is fine. Either one is fine. Okay, we have another complex fraction in the next example. Only one inner fraction. So using the same technique, I'm going to multiply by 2 root c over 2 root c. Notice that multiplying by the LCD of the inner fractions is always going to cancel out that denominator. It's going to get rid of the inside fractions. That's what this technique does. By using the LCD, least common denominator of all the inner fractions, you end up canceling out all of the inner fractions, hence making this more simplified. Okay, so we're going to multiply numerators. We need to distribute. Root c times 2 root c is 2c minus. Then I'm multiplying b over 2 root c times 2 root c. So that gets rid of that. It's just b. In the denominator, root c squared is c. So 2c root c. 2c root c. I will leave it like so. If I wanted to split this into two fractions, I could unadd the fractions. If I wanted to do that, 2c over 2c root c minus b over 2c root c. I could do that, cancel out this common factor. But again, that doesn't really look any more simple to me. So they're both correct, but I would probably just stop here at the first box. Okay, next one. Now we have two inner fractions. We've got this 1 over x, we've got this 1 over y. So using the same strategy we were doing before, we have to multiply by the least common denominator of x and y. Least common denominator would be xy. Xy over xy. Then we're going to distribute. Usually I don't distribute, well, yeah, usually I don't. In the other examples, I didn't distribute in the denominator. I just kind of left it because I was hoping something would cancel because my inner fractions were in the numerator. This time I can see in order to get rid of these inner fractions, I definitely need to distribute in the denominator. So maybe I don't want to distribute in the numerator because there are no inner fractions in the numerator, and I'm hoping something will cancel. It might not. So I might end up having to multiply that out anyway, but for now, I'm going to leave it in the hopes that something will cancel out later. Okay, so in the denominator, now I have to distribute. Do it off to the side if it helps. It's 1 over x times xy, like that. You can see that we're going to lose the x's. It's just going to give me y. Plus, and now I'm multiplying xy times 1 over y. 1 over y times xy. We can cancel out the y's, so it's just going to be x, like that. And as I suspected, now I have a common factor, x plus y and y plus x are the same because addition is commutative for real numbers. Okay, so we can cancel out that common factor, and now we just have xy. Next, inner fraction, 1 plus x over y. So if I want to use the same technique, then I'm multiplying by 1 plus x over y. 1 plus x over y, like so. Numerator. There was no inner fraction in the numerator, so I'm just going to leave it in the same form, like this. Now, I still have an inner fraction, right? Because the thing I'm multiplying by has an inner fraction, so I might have to go further with this. We'll see. And then in the denominator, let's see, we've got this times this. We're going to distribute this whole thing right here. It's distributed to the 1. So I get 1 plus x over y. Minus, and now I'm distributing here, and that's going to all cancel and just be 1, like that. Now, what we cannot do, it might look very tempting. It does look tempting. We cannot cancel here. This is a factor in the numerator. This is not a factor in the denominator. It's not a factor. It's not a factor. You cannot cancel out unless it's a factor. You have to factor out before you can cancel out. So we cannot do that. I still have a complex fraction. I'm going to simplify a little bit more. I can see in my denominator x times 1 plus x over y. In my denominator, I have 1 plus x over y minus 1. So the 1 minus 1 is 0. This is just over xy. Now I could use the same strategy I've been using and multiply by the least common denominator, which is y. So I could multiply by y over y. If I want to do that, I can multiply by y over y, but I see a better way because my denominator has only a single term. Dividing by x over y is the same as multiplying by y over x, the reciprocal. So this is equal to x times 1 plus x over y. Dividing by x over y is the same as multiplying by y over x, like that. Now, this is multiplied factors, so I can write it as one big fraction. Like in the numerator, we have x, we have 1 plus x over y. I have a y, which I can put here. And then in the denominator, this is all over x. X is a factor. X is a factor. These are common factors, so we can cancel them out. So now my final answer, y times 1 plus x over y. And if I want to distribute this y, I think it will look more simplified if I distribute the y. I'm going to have y plus, when I multiply y times x over y, I just get x. So final answer, y plus x, or x plus y if you want to put it in alphabetical order. Okay, x plus y. All right, we're on number 24. Number 24. So number 24, we're trying to simplify. The numerator does not look factorable. And I'm saying that because this is, coefficient is 1 times 1. 4 could be 1 times 4 or 2 times 4, but there's no combination here that's going to give me a 2 in the middle. 1 and 1, 1 and 4. 1 and 4 is not going to give me 2. That doesn't work. 1 and 1, 2 and 2. That's 2 and a 2. It's not going to give me 2 in the middle. It doesn't work. This is not factorable. This is not factorable. The numerator is not factorable. Now, it doesn't mean this can't be simplified. We just can't simplify it by factoring. So what I'm going to do instead is I'm going to split. When you have multiple terms in the numerator, you can split the fraction apart. Don't change the denominator. You cannot change the denominator. You can never split the denominator. You have to keep the denominator the same. All I'm doing is like unadding. Like, what did it look like before you added? Well, we had a common denominator. Before we can add these terms together in the numerator, we had to have had a common denominator. So we're just, oh, that's a minus. Minus 4 over root x. If I gave you this problem and I said simplify it, there's a common denominator of root x, you would just add the terms in the numerator, right, and put it over the denominator. So that's all I'm doing is unadding. But now I can simplify each of these terms individually. So x squared over the square root of x. The square root of x is the same as x to the power 1/2. And then I can use my exponent rule where I subtract exponents. So x squared divided by x to the power 1/2, I'm going to subtract my exponents. It's going to give me x. 2 minus 1/2 is 1.5 or 3/2. Okay, same thing here. Square root of x is x to the 1/2. This is x to the power 1. I can subtract those exponents. So 2x. 1 subtract 1/2 is 1/2, like so. And then the last term, we can't cancel or anything with the root x. So I could leave it 4 over root x. I could leave it like that. But since the other terms I put rational exponents, just to be consistent, I'll use a rational exponent. This is x to the power 1/2 in the denominator. If I move it into the numerator, it becomes x to the negative 1/2, like so. So there's no set rule on, if it says simplify, there's no set rule on like how we would have to write that last term. I just wanted to be consistent with using rational exponents. But I could have just left it as negative 4 over the square root of x. That's okay too. 25, similarly, we're not going to be able to factor the numerator. We're just going to split this up and simplify each term separately. So we have 2x over x minus root x over x plus 3 over x. 2x over x, our x's cancel out, just 2, minus. Here in the numerator, the square root of x is x to the power 1/2. X to the power 1/2. So if I subtract exponents, 1/2 minus 1 is negative 1/2. X to the negative 1/2, like that. And then this is x to the power 1. If I move it into the numerator, it's going to be x to the power negative 1. So if I want to be consistent and have rational exponents, I might write it like this. Typically, we do not leave negative exponents in our answer. I know I did in the previous problem, but again, there was no specific directions on how we were supposed to simplify this. But typically, I will say, we normally do not leave negative exponents in our final answer. So I could write this as 1 over x to the power 1/2, or just 1 over root x, and then 3 over x to the power 1, like this. I think that looks best. Okay, I'm going to pause the video here and maybe make a separate video for the next couple of sections.